Say an AI model learned something it shouldn't have, a private fact, a piece of misinformation, copyrighted text. Can we make it forget? A whole field called machine unlearning tries to do exactly that. But this paper asks a sharper question. When a model unlearns, does it actually go back to the way it was before, or does it just get more confused? Meet RESTOR. Training a giant model from scratch without the bad data is far too expensive, so people use unlearning algorithms instead. The trouble is judging whether they worked. Most papers check two things. Did the model forget the target content, and does it still perform well on unrelated tasks? The authors argue that misses the real point. RESTOR adds a third, tougher demand they call restorative unlearning. If the model truly removed the influence of that bad data, it shouldn't just forget it. It should bounce back to the knowledge state it would have had if it had never seen that data at all. Forgetting is easy. Actively restoring the original knowledge is the hard part. Here's the setup, and it's clever. Start with a clean model. Train it on a batch of documents full of incorrect facts. That gives you a corrupted model that now believes wrong things. Then run an unlearning algorithm on the corrupted model. Question RESTOR measures. Does the unlearned model match the ideal model, the one that never saw the bad documents in the first place? To make this measurable, they build a controlled testbed. They collect 1,051 true facts, about 50 famous people from Wikidata. And they swap implausible but wrong values, say, claiming Nelson Mandela was born in the United States. They ask GPT-4 to write 3,000 passages stuffing in those wrong facts, and continually train the clean model on them using low-rank adaptation. Now the model is reliably corrupted. Now a surprising twist. They control how much unrelated, correct context gets mixed in with the wrong facts, a knob they call K. You might think padding the lies with true trivia would dilute the damage. It's the opposite. More unrelated context makes the corruption stronger. Plain lists of wrong facts barely dent the model. Wrapping them in rich, diverse passages does far more harm. Test 3 popular unlearning algorithms. Gradient ascent simply pushes the model to make the bad documents less likely. KL divergence pushes the unlearned model's predictions away from the corrupted models. And NPO, negative preference optimization, treats each bad token as a negative example to steer away from. All three only get the corrupted model and the bad documents, no access to the correct answers. And here's the headline. Gradient ascent and KL are good at forgetting, but they fail to restore. Sometimes they even degrade the model further. NPO is the standout. It pulls the corrupted model almost all the way back to the clean model's accuracy, regardless of how badly it was corrupted. Remember, it does this without ever seeing the correct facts. Look closer at the facts the clean model knew, but corruption broke. After unlearning, each answer lands in one of three buckets. Recovered the right answer, forgot the lie but guessed something else wrong, or stayed wrong. NPO recovers the correct answer 73% of the time. Gradient ascent. Just 21%, it mostly forgets without recovering. Why the difference? This figure tracks the model's confidence. On the left, the clean answers. Corruption crushes their probability, and NPO restores it while gradient ascent barely moves it. On the right, the random wrong answers. Gradient ascent actually pumps those up. So gradient ascent forgets the lie, but it spreads the probability across other wrong answers instead of returning it to the truth. This is the core insight of the paper. Forgetting and restoring are not the same thing. An algorithm can perfectly erase the bad fact and still leave the model worse off, because erasing isn't the same as repairing. Earlier benchmarks that only measured forgetting and utility couldn't tell these behaviors apart. RESTOR can. Restoration isn't guaranteed, though. The authors find it depends on how confident the clean model was to begin with. Facts the model knew solidly, like a person's country of citizenship or language, come back easily. Facts it was shaky on, like someone's cause of death or awards, mostly can't be recovered. You can only restore knowledge that was firmly there in the first place. They also test a practical fix. If you can isolate just the wrong facts and strip away the unrelated context before unlearning, gradient ascent and KL improve noticeably. NPO, on the other hand, is already robust either way. So cleaner unlearning targets help the weaker methods, but the gap to NPO remains. But there's a hard ceiling. In a brutal stress test, they scramble a model's knowledge so deeply that accuracy on the target entities crashes from 67% to 31%. Now none of the algorithms can bring it back, not even NPO. Once the original knowledge is truly destroyed, there's nothing left to restore. So what should you remember? Unlearning is not just forgetting, it's recovery, and the two come apart. Preference-based methods like NPO can genuinely restore knowledge the model never explicitly relearns. And critically, how you measure unlearning changes which method looks best. Restore gives the field a way to test what really matters. Did the model go back to who it was? That's Restore, a sharper lens on what it really means for an AI to unlearn. If this helped the idea click, consider subscribing and tell me which paper I should decode next.